So good afternoon. Welcome to this presentation. My name is Olivier Crémel. I'm a principal engineer at VMware. I've been working at VMware for the past 10 years since ESX 1.0, and I'm the ESXi architect. And 3 years ago, I actually presented ESXi at VMworld, and a lot of stuff has happened in 3 years. So why did we do ESXi? Our main motivation to do ESXi was actually to address the two ends of the scale. We wanted to make it easier to deploy and manage thousands of nodes because we had in mind the appearance of the cloud. And we also wanted to allow just very small turnkey installation. We didn't really worry about the middle, just those two extremes. So how did we go about it? Well, mainly we wanted to reduce complexity because if it's less complex, it's easier to manage. And the way to reduce complexity is first to realize that we are not trying to do a general purpose computing platform. So remove everything that's not really needed for running VMs. We also wanted to make configuration easier, so we wanted to leverage the defaults as much as possible. Now, it's always easy to say we're going to remove unnecessary things, but what you think is unnecessary may actually be very useful and needed by someone, right? So over the past 3 years, there's a couple of things that we had to backtrack on, and I'll go over some of them. I'll just listed a couple of examples here that you may have in mind already. The TSM, that's the tech support mode, SNMP support, and scripted installation. So for this presentation, I'm actually going to focus on core characteristics of the ESXi platform that are very different from other systems. I'm not going to give you any tips or tricks about storage or networking or how you run some commands. It's really going to be very technical. So I know I did this presentation Monday, and I know I surprised some people with that. So just so you know. There were other presentations. I know it's a little bit late to tell you now because it's Wednesday evening, but there were actually other presentations about convergence and ESXi management in general. Nevertheless, there is just one slide that I was asked to present. It's a summary of some of the issues that some of you may have experienced with ESXi and what we've done to address them. The first one, SIM management. So when we started, again, as you remember for the previous slides, when we started, we wanted to have something that was really self-contained, and SIM really was a great platform for that. The problem is that not a lot of tools, not a lot of OEMs, not a lot of third parties were up to speed for SIM. So it turned out that this was really a little bit short. We've done a lot of work on it. VMware itself has done a lot of work with the SIM, with the SFCB framework, has contributed back to the open source framework. And we've had fairly fruitful discussions and work in cooperation with the third parties that are also going to get there. Nevertheless, we are actually bringing back SNMP. So in ESXi, when it shipped, there was a very small SNMP agent that was actually embedded into the hosted agent. For 4.1, we've beefed that up, and actually beyond 4.1, we'll have a full-fledged SNMP agent. Another aspect that was also mentioned was the lack of Active Directory support. This has been integrated in 4.1. So starting with 4.1, you can use Active Directory for identification and authentication. Two issues about USB. ESXi, again, with the principles I highlighted in the first slide, since we wanted it to be very contained and simple to manage, USB was a choice for that. Unfortunately, the way the USB stick were certified was not rigorous enough, and we've had a couple of instances where the sticks that were being shipped were actually not very reliable. And so OEMs had to ship replacement sticks. So we actually improved a lot on the certification for 4.0, and we believe that we've solved that issue. Related to that was HA. So HA is our high availability product. For 3.5, it actually relied on USB. This was the only component that actually relied on USB, as you'll understand from the next slides. So in 4.0, we removed that dependency, and actually we have completely rewritten HA, and it's a brand new agent that's going to appear after 4.1 that's going to be very tailored to ESXi. Finally, the two issues that are more kind of abstract but very important, extensibility and supportability. Again, since we wanted ESXi to be simple, we wanted it to be fairly closed in the sense that you could not get in the inside of it. And so we relied on the Vim API for any kind of extensions. Unfortunately, again, a bit the same as SIM, this was a little bit ambitious because not a lot of people and third parties were actually full speed on Vim API at the time. It's much better now. The firmware model also that we introduced, although it was well suited for the small and the very large, is not really that suited for the people in the middle. So two things that we've added is a scripted install, which is available in 4.1, and what we call the image factory, which is basically a way for customers to tailor their installation and create system images. Supportability, so there was a couple of issues there. There was a bit of misunderstanding about the way the system worked, and we ended up with a lot of people not realizing that their log would not persist. And so getting into trouble and then calling VMware support and then realizing they didn't have any logs to describe what happened. And finally, we were not extremely clear about what we would allow people to do with the TSM, the tech support mode, the shell that you had to go and type blindly unsupported before something appeared and you could do something. So we actually clarified, and I'll talk about it in the next slides. So anyway, so that's the background. Now, I'm going to talk about three things that are kind of very ESXi specific, and that it's very important to understand how they work because it has some impact on the way the system behaves, and it really can be very helpful if you get into trouble. The first one is going to be about the files and the file systems and how the system is organized. The second part is going to be about the agents and what we call the user worlds and how those things run on ESXi. And the third one will be about the TSM and what you can do and what you have available in there. So ESXi is based on what we call a system image. We used to call it firmware, but it was kind of misleading, so now we call it system image. It's an essential concept of ESXi in the sense that there is no concept of installation as far as ESXi is concerned. When you use the installer for ESXi, if you want to put it on a disk, the installer, actually what the installer does, it takes the system image that would normally be shipped on USB, it just dumps it as is on the disk, and it's done. It doesn't do anything more than that. That system image is actually unified. We have a single system image, so that's the same system image that would be on a USB key. That's the same system image that you could boot from Pixie or from anything else. We have logic in the first boot where we actually go and try to figure out what kind of installation we have, and we do auto configuration based on that. One thing that's important to remember is that ESXi is memory-based. So that means that when you boot the system image is delivered, whichever way, and then that system image is entirely loaded into memory. And from then on, we don't go back to the boot device. We don't care if it's there, if it disappears, if it fails, if it's removed. It will not affect the system. Important to note is that because of this, each time you reboot, you always get back that same image. So modifying the system means modifying the system image, not doing stuff to the file system itself. If you go into, I'm pretty sure some of you have tried, if you go into the shell, the TSM, you change some files, you reboot your machine, and you realize everything has disappeared. It's going back to the way it was. The important thing about this is that it means that you can always track the state of your system, the level at which it's at, the patches, everything, just by tracking the system image. So what is that system image? The system image is a collection of files, an ordered collection of files. We have a series of executives. So those are basically what you would call the kernel. They are loaded in memory, and they don't show up in the file system. Then we have a series of archives. Those archives come from the VIBs. Now, the VIB is, if I remember correctly, VMware installation bundle. It's equivalent to an RPM, if you're familiar with Red Hat. It basically contains components, dependency rules, stuff like that. Only the archive ends up in the system image. So if you look at the bootline command, you will see those names, for instance. System is for the core system. VPXA is the agent that VC pushes on the system. AM is the high availability, etc. Those archives are used to make up the file system. After that, we have another archive that we call the state archive. It's present if the system is stateful, which is the default. So today, if you use ESXi, unless you boot Pixie, you are running in what we call the stateful mode. That archive contains the exhaustive state of the system. So again, this goes to the previous slide with the system image. You can completely define your system with just two elements: what system image you've booted from and your state archive. You can take that state archive, you can put it on another machine, provided that other machine is similar in hardware, and you will get back exactly the same thing. As a final point, I said that, well, I know some customers have done it. If you are bold enough and if you follow what's going on, you can actually add your own archives there and customize the system. That's purely unsupported. That's not the way to do it, but it's some things that some customers have done. So those archives that I just described, we call them Tardisks, mainly because they're simply a tar archive. They are the standard tar archive. We have a special format, but it's very close to the main format. We call it vmtar. There is a command actually in the shell that you can use to create those. It's not required. That is, you can always use standard archives, but those modified archives are actually, I don't know if you're familiar with the tar format, but the tar format aligns everything on 512-byte blocks. Now, we need to page align binaries if we want to be able to page share and reduce memory consumption. So for the big archives in which we have a lot of binaries, we use this special tool to kind of modify the layout so that we can then reuse the pages. So those tar disks are what we call mounted in the file system. And you can think of it as a combination of untarring and loop mounting. It's untarring in the sense that all the files suddenly appear everywhere in the file system depending on their path. But it's also loop mounting in the sense that they still remain linked to each other and to the Tardisk, which means that we can actually undo this operation in just one other operation that we call unmount, which means that if you install VIBs, and if you later decide, I don't want that one, and you uninstall it, it just disappears, and the system is exactly back to the same state it was before. In particular, there is something very important about this, is that the way it's done is basically we overlay the Tardisks as we get them. So if you install a VIB that, for instance, has an updated version of a driver, this will overlay the old one. The old one will disappear. As far as you know, and if you go into file system, you won't find it. There is no way to find it. It's hidden, completely hidden. But if you uninstall that VIB, then that old driver will suddenly appear back in the file system. So this is a very important property for us because it means that installation and uninstallation is a completely symmetrical operation. So what about the state? So the state Tardisk is actually a collection of state files that we like to persist. How do we choose those files? Well, those files are all the files present in etc that have been marked as sticky in one of the Tardisks. Now, what that means is that when we create the Tardisks for a component, let's say for VPXA, the VC agent, in that Tardisk you will find the binaries, but you will also find the default config file. And that default config file will have the sticky bit. So this, I don't know if you're familiar with the sticky bit, but the sticky bit in Linux or Unix or POSIX systems is a special protection bit that you can set on any file. Now, we don't use the semantics, the usual semantics. We kind of hijacked it for our own purpose. But we use that to basically tag a file as saying, this is actually a state file. Any other file in the system that is not under etc, or that is under etc but is not tagged with the sticky bit, will not be persisted. So if you go into the TSM and you find a config file that you don't like and want to modify it, if you modify it and it's not something that we said it's a config file, then when you reboot, your modifications will be lost. Important thing to note about this is that this is a Tardisk like the ones I described earlier, which means it's in memory, which means everything happens in memory. So how do we persist the state? Well, persistence simply means that we have to constantly rebuild and save that state Tardisk back onto the boot disk. This is actually done periodically. There is a daemon in the background that every 10 minutes go around and looks and say, has any of the config files changed? If it has, then I recreate its state Tardisk and I put it back on the boot disk. Now, why is it done this way? Well, the motivation is the USB flash device, right? Since we started with that, we could not constantly write to it each time something changed because the USB flash would have possibly be worn out in a matter of months. So based on calculations, discussions with the USB flash OEMs, we came up with that 10-minute window. Which means there is a window, 10-minute window, during which the state that's in memory may not be the same as the state that's on disk. Which means that if, for instance, the state was committed to disk, the 10-minute window starts, you do some more modifications, the state is reflected in memory, and suddenly your machine crashes. There's a PSOD. You're down. When you reboot the machine, you will get back to the state that was at the beginning of the window. Now, since our system almost never crashes, that's not really a problem. But if it does, the most common thing that happens is VM registrations. The most common thing that's lost, because that's the thing that changes the most often, most of the state is actually pretty static, is the VM list. So what you may end up with is if you just added some VMs or registered some VMs and you had this crash, when you come back, you'll see the VMs as orphaned because the host has no memory of the fact that you added those VMs. I should note that we have an API, a Vim API, that is used to save and restore the state. You can go and you can actually use it to back up your machines. And that's simply what that API simply does. It just makes a copy of the state tardisk. So when you use it, what you get is a copy of the tardisk. And when you want to restore, what it does is simply takes whatever you give it, puts it back on the machine. So a quick word about stateless and diskless, since we talk about it quite a bit, but we rarely say what we mean by it. What we mean by diskless is simply no boot device to go to. It doesn't mean you don't have a disk, right? So what we mean by diskless is that the system itself has no backing. The typical example is Pixie. You may have a machine with a couple of disks, but if you boot from Pixie, those disks are, as far as the system is concerned, are not part of the system. You may create VMFS on it, you may put VMs on it, but that doesn't concern the system, because that's data, that's not system operations. I should note, an important point to note is that USB, if you boot from USB, that is your disk. So if you have a machine with no disk, but you boot from USB, then we are telling you you are actually disk full, because we go back to that USB, right? So what do we mean by stateless? Now, stateless means simply that the state authority is not ESXi. It doesn't mean there is no state. There's always some state somewhere. I mean, you need to know the name of the machine, the IP address, whatever. It simply means ESXi is not the authority. Someone else keeps track of that state. So if you have a diskless system, so again, that's typical example is Pixie, then we don't persist the state, because the state will always be persisted back on the boot device. So if you have no boot device, we don't persist the state. That's what we call stateless. If the system is not diskless, and that's pretty much everything you're running, then the state is persisted on the boot device. Now, if you are stateless, where do you get the state from? There are two main ways you can do it. And we have had customers who tried both ways. I mean, some customers went one way and some other customers went another way. The first way is the most obvious way, is to say, okay, your state is a state tardisk. Well, I just need a way to give it to you, right? So the way I can do it is I can just manufacture one. I know what I want in my password file. I know what I want in my hosts file. I just create those files. I tar them up. I say, this is your tardisk. And I just put that tardisk on the same list of tardisks that are going to be used when I boot. So if I boot from Pixie, at the end of the Pixie boot line, I add the tardisk I just created. And when I boot, it will get pushed on the box. And the box will have the state I decided. Now, obviously, the box itself will not be able, if there is update of the state on the box, it will not be able to update it back. So you have to manage it. Another way, which is the way we actually support, is to use host profiles. So instead of having kind of a passive implicit configuration where you basically, when you get up, your state is already there, you didn't do anything special, you have an active kind of explicit way of doing it. What you do is that you boot ESXi with a default configuration that's minimal. And that configuration simply allows ESXi to wake up and say, okay, I just booted, I don't know what I'm supposed to do, why don't I talk to this guy? And so ESXi goes and talks to the guy and say, I'm up, tell me what to do. And then that guy basically uses Vim APIs and says and does calls. Say, okay, this is going to be your VM list. This is going to be your vSwitch configuration. This is going to be your LANs, whatever. Right? So we have an implementation where VC, Virtual Center, is acting as that third party, third entity. You can boot ESXi from Pixie. We'll give you the default state. You just basically tell where is VC. And ESXi will boot, will go back, talk to VC, say, I'm here. And then VC will just do normal Vim API operations, saying, okay, oh, you're here. Okay, this is the IP address I want you to use. This is the VM list I want you to use. This is the lens I want you to talk to. This is a very flexible way of doing it, especially if you use the full power of the host profiles. But it's very different from the other way, in the sense that you have an ESXi system that for a while is not in the state you want it to be. So you have to be very careful about what you do with it. Right? I'm going to give you an extreme example. You could say, I'm going to boot with no password, and I'm going to use host profile to set the password. That means that you have a window during which ESXi is up with no password. Okay, so we've defined the Tardisk. That's the static content that's actually frozen. You are not allowed to modify it. The config files, the one that have the sticky bit, actually when the system modifies them, what happens is that actually a special copy is made. The original is never modified. We have a special copy that's made. We call that branching. And all those files that are kind of created during the life of the system are actually stored into RAM disks. Those RAM disks are, they have nothing special about them. They are the usual RAM disk you may be used to. They are mounted at a fixed mount point. We define a minimum and a maximum. So we define the amount of memory that you will always get and the maximum memory that you may get. They actually use the memory if they need to, but if they don't, the pages are released. Both the Tardisks and the RAM disks are tracked with resource pools. And I'll come back to that in a little minute because it's important. So anyway, this is basically what it looks like. You have your file system, you have your files. Some of them come directly from the Tardisk, which is basically loaded in memory as the tar archive and kept as the tar archive, so they are just one big block. And some of them come from RAM disk, which is just a collection of pages, so they are allocated page by page. So there is an example of a config file, etc password. So the original become pound hash, dot pound, and the copy with the real name comes from the RAM disk. So that's what I was, so I don't know, it's a little bit small, but this is, I will come back to this slide for the agents also. This is something that's very interesting. I don't know if you've ever looked at it, but this is a very interesting page if you want to figure out what's going on in the system at any given time. That's the resource pools page. So you get to it by going to the system resource allocation, and then you click on advanced, and basically what you get is a tree, a graphical tree of all the resource pools in the system. And it's divided into different categories, right? And if you look at this one, so if you go down the kernel part of the tree, at one point you reach what we call VisorFS, which is our file systems. And under it, you have all the resource pools for everything that makes up the file system. You have the RAM disk and you have the Tardisks. And since they are normal resource pools, you have the same kind of characteristics that you would find on any other resource pools. In the case of the file system, a CPU is kind of irrelevant because it doesn't consume CPUs, but memory is interesting. And you can see that this one, main sys, which is our main RAM disk, you can see that it has a reservation of 32 megabytes and a maximum of 32 megabytes, which means basically we are reserving 32 megabytes for it, and it's guaranteed that it will have 32 megabytes and it will never have more than 32 megabytes. Now, what's interesting is that you can actually modify those numbers. And I'll come back to that in a little minute because it's interesting for troubleshooting. Likewise, we have a command. You can get to in the shell. So we don't use the normal DF because our semantics are very different from the normal disk semantics, so it doesn't really fit. So we have a special command that's called VDF that basically gives you the utilization. So you can see, for instance, the one I was talking about, 32 meg of minimum. You can see how much has been used. You can see the peak, and you can see how much is available. Now, a good example of another one is TMP. It has actually a minimum of 2 megabytes and a maximum of 192. Currently, it's barely used. But what is interesting is those two columns. It means that you can get 1 meg, that's sure. You will always get that because you can have 2 meg maximum, right? But the 192, it's a maybe, right? So if there is no memory available, then the SRAM disk will not be able to grow. Same as DF, another very interesting one is DU. So we have the VDU. And the VDU will give you where all the files are coming from. So you can see that in etc, for instance, we have 312 files that actually come from the main system Tardisk. We have 6 files that comes from the VC agent. And we have 38 files that actually have been branched and actually reside now in the RAM disk. Here is one example. The default DH client leases is an empty file, but someone has already gotten some leases, so this is actually the current state of that file, and you can see the capital T here. That's the sticky bit I was talking about. So what you get in the RAM disks is the branch state file, as I said. But there are also 2 other things that are very important. It's the logs and the core files. You have logs going to varlog. Varlog is in the main RAM disk. That means it's in memory. That means if you reboot, it's gone. So if you have a problem in the hostd, for instance, that doesn't bring down the machine, you would have to go and get the logs before you actually reboot. But if you have a PSOD, well, then you're out of luck. So obviously, that's less than ideal for most deployments. And what we have is actually a syslog daemon that which can be configured to actually redirect the logs to anywhere. So in the default installation, if you have disks, on the first boot, ESXi will actually be smart enough to find a disk, create what we call a scratch partition on it, and then use syslog to redirect your logs to that partition. This is actually something we introduced in 4.0. In 3.5, we actually relied on people to do it. We basically said, okay, you need to configure syslog. Unfortunately, I mean, it's kind of difficult to rely on people to actually read all the documentation and for those kind of things. This is really something that we should have done automatically, and that's what we did for 4.0. So there are a couple of things that can go wrong with the file system. I mean, if you've listened to what I just described, you can already think, okay, I can imagine this would go bad here or there. The main RAM disk, for instance, the one that's guaranteed 32 meg, well, that size has been done so that it's based on what we think the system will need. But we don't want to waste memory, right? So we sized it so that during normal usage, it's completely expected that it would be 95-98% full. We only expect it to run out of space if there is a bug somewhere or if someone does something that's not supported. I give you an example. That's something that happened that we had SRs about. You go into the TSM, you go into the shell, and you think you need some command or want to do something, and you SCP a file inside the system, or you create a file. or a 2 meg binary or whatever, and you put it in slash or whatever, and suddenly you've taken 2 megs out of the 32 meg that we never expected you to take out of. You can track usage, as I showed you in the slides, not only about the VDF command, but also the GUI. And since it's available in the GUI, it's also available as a Vim API. You can do it remotely. You can actually track what's going on by just tracking the resource pool stats. You can know at any given time what's the current usage, what's the peak usage, and you can monitor those file systems this way. Now, running out of space in this main RAM disk is actually very bad. That will make the system very unstable. One of the reasons is that all the config files are in that file system. And one config file, ESX.conf, is the main way with which hostd keeps track of what's going on. So each time you do a hostd operation, even if you don't do it directly, there is probably going to be a I/O operation on ESX.conf. If it cannot be written because the main RAM disk is full, then most likely, I mean, it's getting better now, but most likely in the past, what you would have had is hostd just crashing or hanging. You can find out about this kind of events. Well, if you've looked at the resource pool stats, if you monitor them, you will see that. You can also see in the logs, you would get error messages about flushing. And now we have also events that will actually go up to VC to tell you something is going wrong there. So how can you get around this kind of problem if you find it's happening on your machine? Well, first is make sure it's not because of you. So make sure someone has not actually gone and done something stupid on the file system. Second option is there is a certain number of files that are definitely not needed for the system. That's the log files in varlog, so you can always go there and make some space. But another way that's interesting is if you get into that system, you've talked to VMware support, they tell you, we are sorry, there's a bug in hostd that causes this, you'll have to update to patch whatever, or wait till update 1 or whatever. In the meantime, there is actually a very simple action that can be done. It's simply go into the resource pool and give more memory to that RAM disk. Same situation with temp, although with temp it's not as dire because temp is actually not vital for the system. As I showed in the slides before, temp is also not guaranteed memory. So at any given time, only 2 megs are guaranteed for temp. If your machine is overcommitted and suddenly you want to have stuff go into temp, they may not go there. So that's again, you can look at it with the resource pool, see what's going on. You can increase the memory. There is one important thing to know about temp and scratch. So I talked earlier about scratch. Scratch is a partition that we create on first boot if we find a disk. And we redirect a couple of things to that partition. Basically, big things that it's nice to persist, but are not really essential for the system. So I gave the example of the logs. There's also the example of the user role calls. But there's also the example of the diagnostic bundle. When you go into the VI client and you say export diagnostic bundle because I have a problem, this will actually get generated in Scratch. Now, if Scratch has not been configured automatically, for instance, because you didn't have any disks available when you install ESXi and ESXi could not do it automatically, then Scratch is transparently redirected to temp, which means that you can get into a catch-22 kind of situation. If you have a problem, because temp is overflowing, and you go into the VI client and you say, generate the diagnostic bundle because I want to know what's going on. Well, that diagnostic bundle is going to get generated in temp, where you have no space. So it will not be successful, and it will not be generated.
Question.
Yes?
The temp is periodically cleaned up, the logs are not. So therefore, the system remains up for an extended period of time, a year, 2 years, whatever time it is, or if there's excessive problems that are being driven from the log, I will have a problem if you have
The logs are rotated, so they do not grow indefinitely. There's a rotation policy. Yeah, so basically you have I don't remember offhand, I think it's 10 files of 2 megs or 20 files of 1 meg, whatever, but they are rotated and they cannot grow indefinitely. So once you reach the steady state, they always use the same amount of space. Another aspect that's interesting to remember, again, since we are memory-based, when you install a new component on a live system, that means you're going to do some memory operation. That component will have to go into a Tardisk, it will have to go into a RAM disk, it will have to be installed in the memory. Which means the memory needs to be available. Which means it's actually better to install or make modification to the system if the system is not overcommitted. Because it's overcommitted, you may get into a situation where the installation will simply fail, saying, sorry, I don't have any resources. Now, there is a very interesting case related to that people sometimes forget or simply don't know about, is that when you have a machine and you connect it to VC for the first time, what you're doing is actually you're installing on that machine a VC agent, which means if you have a machine that's overcommitted and you have not added it to VC yet, and you want to add it to VC, VC will try to install that component. But if the machine is overcommitted, the memory is not there, that component cannot be installed. And so you'll get a failure to install, and VC will complain that it cannot connect to the host. So just a quick note about, since I keep saying we are in memory, we don't rely on disk, what actually do we rely on disk for, on personal storage for? So as I said, nothing for the file system and ongoing operations. To persist the state tardisk if you have a boot device, and also to persist the logs, the core dumps, and the diagnostic bundles. So that's the one I was explaining earlier. If we find that you have a disk, we'll have a scratch partition, and we'll put all that on that scratch partition. So just a couple of slides to illustrate this. So again, you have the file system. So I highlighted 4 interesting pieces. The boot bank, which is basically the directory in which you have your system image. The locker, which is a directory in which you have the VI client and the VMware tools so that you can download the VI client from an ESX host or install the VMware tools. The scratch, where you would put the logs, the user role core and diagnostic bundle, and the temp. So this is the default for most of the machines that have been installed or use USB, and for which a disk was found. So we were able to create the scratch partition. We had the boot disk, and basically the boot bank goes to the boot disk, the locker goes to a special partition, the scratch goes to the scratch, and the var temp always goes back to scratch, right? And for temp itself, you pretty much have no use. So that's actually the ideal case if you're concerned about memory.
Question?
Yes?
How can I verify if the scratch partition is there or not?
So this actually is configured as you can look in the UI. It's a normal config parameter. It's under advanced config. So if you go in the UI, or if you use the Vim API, if you use the commands, and you look at advanced config, one of them is called scratch. And it will point to whatever has been set up. And you can actually change it. It doesn't have to be, so by default, as I said, ESXi will try to create a partition. That's actually a 4 gig VFAT partition to put it on. But you can, if it hasn't done so, or if you don't like it, you can redirect scratch by modifying that advanced config option to whatever you want. You can make it go to a LAN, you can make it go to an NFS mount partition, you can share it between different ESXi hosts. Like you can have a big LAN that you say, okay, that's for stuff I don't really care about, and you can have all your ESXi hosts go to that. So if you don't have that, if it hasn't been configured, then this is what I told earlier, the scratch will go there. if you don't have a boot disk, so this is, for instance, if you PXE booted, then what happens is that you don't have this. So this locker is redirected here so that we have something to hang on to, but the content of it is not duplicated. So if you PXE boot, you don't have a VI client and you don't have VMware tools on the machine itself. And finally, if you PXE boot and if you don't have anything configured, then everything ends up here. So that's it for the file system. Agents. So what are we running on ESXi? We are running the core executive, that's the VM kernel. We are running extensions for it, that's the kernel modules, that's the driver. And we are running schedulable entities. And we call them worlds. That's historical. That was to make a difference between processes that were running in the console OS when we still used to have the console OS. So we call them worlds, and there are different types of them. We have system worlds. We have the VMM, the world, which is the main engine for the VMs. And we have what we call user worlds. Now, user worlds are simply worlds that don't have system privileges. They have nothing to do with the end user or the user. It's user in the sense, not system. Those user worlds are have access to VM kernel system calls, some of them virtualization specific. They also have access to a fairly large subset of the POSIX system calls. That's why we're able to run most of the commands that you are used to on POSIX systems. They are not swapped. Again, I go back to the reliance on disk. We don't swap our user worlds. Which means, again, that the whole system is memory-based. Which means that if you lose your boot device, as I said earlier, the system will not be affected. This is interesting because we have with classic ESX, since the service console is swapped, we have SRs of customers being annoyed by the fact that when they get into a APD situation, they've booted from LAN and they get all path down on the LAN, and ESX has no longer access to its boot disk, then ESX and the service console will freeze and may crash and hang. And that's because it swaps. Since we don't swap, we don't have this problem. The same way that I describe RAM disks and Tardisks being tracked by resource pools, our user worlds are also tracked by resource pools. You can think of them as some kind of very specialized VMs that have a very special environment. But from the outside, you can kind of do the same thing you would do with VMs. We have page sharing between the user worlds. We have the resource pools. You can say, okay, that agent, I don't want you to use more than 100 meg, or I want you to be sure you have at least 32 meg. Or I don't want you to use more than one CPU of power, or something like this. So again, I go back to this slide of the... so that's the same tree, advanced. But further down in the hierarchy, there is one called VMvisor. That's the main group for all the user world. And you can actually you can look at it. It's dynamic. It's actually very cool to look at because it's, in a sense, it's a graphical PS3 of what's happening on the system. So you can find everything that's running on the system is there. So they are grouped into different categories. Again, it's hierarchical, so we create resource pools and we give them CPU allocations, memory allocation, and we do it based on what they are doing. So for instance, we have a special pools just for the plugins so that we can actually constrain the plugin so that if a third-party plugin misbehave, it's actually contained in there and doesn't affect the rest of the system. This is one example. So if you go down, there is hostd. That's our main agent on the system. we can see that there are actually two worlds making up host D. And you can see that for host D, for the group itself, there is also numbers associated with the process. But for the group itself, we have put a cap of 495 megabytes. That is, if host D has a memory leak or whatever and starts consuming memory like crazy, it will actually get capped at 495 and get killed and restarted if it hits that limit. Same thing with the third party. So this is an example of a plugin. This is the Emulex SIM provider. And you can see that this one is actually limited to 82 megabytes. So this is very important because this is very different from the way agents work in other systems. The agents that run in the service console had this illusion that they could have all the memory they wanted because the OS is actually doing it for them. And when you run out of memory, what happened is that the system would come in and say, okay, I'm out of memory, I need to kill someone, pick someone randomly and kill it. We had issues with that because most of the time, I don't know, maybe it's against VMware or something, but it would always pick host D to kill for some reason. So when we're running as user world, this is a very different environment. Those agents are memory constrained. If they want to get memory and they have hit the ceiling, we simply tell them, well, you get null or you get inomem, right? The problem is that some of them we just got from the service console and they haven't been properly taught yet how to behave correctly. And when they get into that situation, they will crash or hang. But the interesting aspect of it is that if we do have someone misbehaving, then it will be the one dying. It will not affect the other ones. You should also note that we have the same thing about the CPU. It's not only about memory, it's also about CPU. So the same way, we have CPU allowances. Again, if a daemon misbehaves and starts consuming all kind of CPU because it's stuck in an infinite loop, it will actually get capped and will just stop getting scheduled. So we have the same. So what can go wrong? Well, the same thing can go wrong that I just explained with the file system. We size the resource pools depending on expected activity. So when we boot, we look at how much memory is in the system, how many CPUs, how much VMs we think can run on that system, how it's been configured. We know the memory usage of our agents, and based on that, we size the resource pools. So if you add memory, or if you remove memory from one to the other, you may have different size resource pools, right? And the same way, you can track them. So you can do resource pool statistics. You can monitor them with the Vim API if you want to. You could look, for instance, at host D resource pool and track the current usage and the peak and maybe send an alert when you find that it's close to the top. And you can also modify the resource pool. So even though we configured them based on expected usage, if you get into a situation because there is a bug or because whatever, again, as I said about the RAM disk, you may, after talking to VMware support or even by your own accord, you may go in and say, I'm just going to give a little bit more memory to host D because I think it's really close to the max. That also applies to the CPU. Host D may appear sluggish. It may be because the resource pool allocation for the CPU is actually too small. You can track that for the resource pools also. You can see, okay, how much memory has it been allocated, and how much CPU has it been allocated, and how much is it actually using. So there is a tool that's actually very cool to look at this. It's memstats. And you get it from the debug vib. The debug vib is a vib that's not installed by default. So you need to get it, and then you can install it on your machine, and it gives you a bunch of new commands that you can access from the shell. And you can see, for instance, if I look at hostd here, you can see it will tell you, well, this is the max that has been granted. And this is, for instance, what's consumed right now, 67. And this is the peak, 71. So you see that this is a machine I probably just booted, so it's fairly quiet. Okay, so that's a good transition to the tech support mode, right? So this slide is about the theory. That's the 3-5 days. That's what we thought could be a viable solution. You manage the system, and you look at the system by using the Vim API, by using the VI client, by using the remote CLI, by using the PowerShell CLI. You do everything with that. If for some reason your system is unresponsive or unreachable, if you have networking issues, then you go to the DCUI. That's the intent of the DCUI. The DCUI is the yellow local console, direct console user interface. Its purpose is very simple. Its purpose is to allow you to configure the network, because obviously to be able to talk remotely, you need to have the network going. So you can kind of do small troubleshooting there. And also to bounce the agents. I mean, again, if you want to talk remotely, hostd has to be up, so you can go in and kind of kick it and see if it behaves better. But once you've done that, you're supposed to go back to using the remote tools. If that doesn't work, if you're still stuck, then the next step would be to call VMware support. And then VMware support would tell you, okay, you can do this magic thing. You do Alt F1, you type unsupported. You won't see anything, but don't worry. I spent a week with our VMware support a couple of months ago, and they told me about how cool it may sound in practice, in theory, but how bad it is in practice. And they told me the story of a customer they had who could not speak very good English, and it took them 1 hour just to get the unsupported shell up, because he was typing, he would not see anything, so he would not understand what was going on. So in practice, we realized that this is really a little bit too radical. The remote tools tend to lag, especially because the problem that you tend to troubleshoot are linked to newer features for which you just happen to don't have remote tools. Also, we have a lot of customers who have existing procedures that require them to do a certain number of things that cannot be done with those tools. So in 4.1, we actually changed our stance on the tech support mode. Now you can actually enable it directly from the client UI and this UI. So VM support is very glad about that, because they can go to their customer and say, just go to the UI, click that box, and that's it. Then the shell will appear. There is no longer unsupported to type with no echo. You just get there. We even made SSH available that easily. Now, obviously, I'm not recommending you all turn SSH on, but you can now actually turn it on by just going to the services pages in the UI. So, that being said, you have to remember that we basically are giving you access to a shell that is very dependent on not doing anything bad in it. I mean, it's not a shell that is foolproofed so that whatever you do, you will not take the machine down. It's still a last resort kind of way of looking at things, and you have to be careful about what you are doing in it. So 2 things you have to remember, and that's why I spent so much time talking about it. It's the file system semantics and the user role semantics. File system semantics, remember that your RAM disks are being sized for a certain usage. So if you need to put stuff in the system, well, be careful where you put it. The best thing to do if you have to add stuff to the system would be to actually have an NFS mount something and put that in an NFS mount and just use that and not do anything in the RAM disk. Also, don't expect any changes you will do to the file system to survive reboots. Because, again, what you see in the file system is what has been loaded during boot. This is not actually what's going to be loaded again the next time you boot. User world. Again, the shell resource pool. So when you go into the TSM and when you go with SSH, you land in the shell resource pool. Now that resource pool has also been sized based on what we think is acceptable. If you start running a lot of commands in it, you may get into a situation where you will get the cannot fork errors, where basically you've run out of the resources there. If you do a lot of CPU-intensive operation, the same thing. You may get into the CPU cap that's on the shell resource pool. So you have to be mindful on that. And you may actually, if you know what you're doing, if you think you really understand what's going on, you may actually go and look at the resource pools and change them depending on what you want to do. I mean, if you have a script that you want to run in the TSM, you're sure you want to do it, you know what it does, blah, 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 but you need more memory or whatever, then you can do it this way. Another thing to remember about the shell is that it's not a general purpose platform. I mean, you cannot expect to run GCC in it. It will work. We actually have daring engineers at VMware who actually run GCC in it. But that's not the intent, right? Also, the commands may appear and may be in reality different from what you are used to because of the way the semantics of the system are, right? I gave you the example of the df and du, where we actually have our own commands. PS is another example. The PS output is different from what you may be used to because the way we manage the world is different from regular processes. We also, as you are probably all well aware, we use BusyBox as the source for most of our day-to-day commands. And this is a small implementation of those commands. So you may have options that you're used to with the normal GNU utils commands that we will not see there, or that they will behave differently. Another thing I mentioned earlier, the debug vib. If you find that you need to troubleshoot in the TSM, then it's very interesting to get that debug vib because you get a bunch of other commands that you would not otherwise have. So what's the cost? Why is it not shipped by default? The reason is simply memory, right? Since everything is in memory, if you install the debug vib, you are burning memory just to contain those commands locally. I don't remember how big it is these days, but it's probably in the order of 40 or 50 megs. Finally, there is a blog, ESXi blog, on the VMware website that's actually quite interesting. I don't know if you've looked at it in the past, but there is lots of interesting information about the shell in there. So anyway, that's it for now.